What I would like to talk about is some construction of exotic four-manifolds, and this time not simply connected with some fundamental groups. So the motivating question is, in differential topology, is given a topological manifold, how many distinct non-diffeomorphic smooth structures can it support? And so today we will just sort of concentrate on connected and compact, no boundary, and oriented manifolds. And we all know the classical results. If the dimension is at most 3, then all manifolds admit a smooth structure. Those smooth structures are unique. And those are important facts. For example, the relatively recent resolution of the three-dimensional Poincare conjecture exactly rested on the idea that every 3-manifold admits a smooth structure, so you can sort of use advanced techniques of analysis. In dimension at least 5, the number of smooth structures is always finite, and we know the classical examples, like the 7th sphere has 28 different smooth structures. And so the list is incomplete. There is the dimension 4 which is missing, and so we don't really know the answer there. So here is my potential answer, maybe, that every topological four-manifold which has these properties, connected, oriented, and no boundary, it either does not carry any smooth structures, we have examples of those, or it will carry infinitely many. Usually I also add the potential answer to be 1 out of respect to the smooth four-dimensional Poincare conjecture, but now I don't really believe in that, so we just skip that. Okay, so that's, no. It's a belief anyway, so it's like we could vote, that's also, that would be very democratic, but we don't do that. So I should add not anymore, but okay. Let's go back to mathematics. Okay, so this is a potential answer to this question. We don't know much about the answer for the simplest four manifolds. For example, the 4th sphere S4, the 4 torus, which is just the fourfold product of the single compact closed one manifold. We don't know it for products of surfaces, and CP2. We do know examples when the manifold admits, the topological manifold admits infinitely many distinct smooth structures. For example, if we take CP2 and we blow it up in at least 2 points, then the answer is yes. We know the answer for the K3 surface, that there are infinitely many. Of course, I should add that infinity in this context is always countably infinite because of some set theoretic reasons. A compact four-manifold or a compact manifold can admit only at most countably infinitely many distinct smooth structures. And there is no example for which we would know that it's smoothable and it has finitely many smooth structures. So yeah, that's the situation now. And so we would like to work towards this sort of red displayed sentence of taking circles of manifolds and trying to verify this potential answer. Okay, the most important invariant of a topological four-manifold, besides its fundamental group, is its cohomology ring. And from the cohomology ring, probably the most important portion is what we call the intersection form, which just takes 2 second cohomology classes, takes its cup product, and evaluates it on the fundamental class, which is now given since we always assume that the manifold is oriented, so that's always fixed. And these forms have a sort of nice classification, and if this is a symmetric bilinear form, which happens to be unimodular, which means that there is for a basis, the determinant of the corresponding matrix is either +1 or -1, and they form a pretty nice sort of circle of forms, provided we assume that they are indefinite. they are classified by the rank, so the size of this matrix, the signature, and the parity. And we say that the form is even if all squares, all of these cup squares are even numbers, and otherwise we say that the form is odd. If the form is definite, then it's a zoo. It's much more complicated. It leads to complicated number theory, and we always say that, I don't really remember the exact numbers, but if the rank of the form is 40, then there are at least 10 to some huge number like 80 or something like the number of atoms in the universe or something like that. But there is sort of a great news due to Simon Donaldson from the early 80s that among those definite forms, in terms of smooth four-manifold topology, only two are really playing a role, and these are the positive and the negative definite diagonal ones. So that's sort of a relief. And so this tells us that if we have an odd intersection form, then it should look like in an appropriate basis as a diagonal matrix, some number of ones and some number of minus ones in the diagonal. Okay, so here is the main theorem. I would like to indicate some steps in the proof. And this is a joint work with Inanc Bajkur and Zoltán Szabó from last year. And I should mention that this whole idea of thinking about, actually think about four manifolds with non-trivial fundamental group. I should admit that for a while I really thought that there are only simply connected manifolds in the face of the planet. But there is this paper of Adam Levine, Ty Lidman, and Lisa Piccirillo, where they constructed an example of some of these types, and this was very inspirational for us. And we started to talk with Zoltán about these constructions, and then 2 years ago, or 1.5 years ago, in the Stanford meeting of the collaboration in December 23, we started to collaborate with Inanc, and it led to the theorem you see on the screen. So it says that if we have a topological four-manifold with the previous properties closed and oriented, and it has a cyclic fundamental group, and for some strange reason, the order should be even but not divisible by 4. And we also assume that the intersection form is odd. So this just means that there is a homology class with cup square and an odd number. Then with 7 potential exceptions, so there are 7 cases for every fixed m where we don't know what the answer is. So they might be exceptions. I strongly believe that they are not. If the manifold is smoothable, then it admits infinitely many smooth structures. So sort of order, reversing the order, let me just mention what are the exceptions. So the exceptions are all of signature 0. So you can see that they are all topologically, they can be written as a connected sum of some copies of CP2, some same number of copies of CP2 bar, and some little four-manifold which brings in the fundamental group. This is what I call an L for m plus 2. So I will just give you the definition of these L's in the next slide. For L2, the definition is pretty simple. We just take the antipodal map on S2. That's an orientation reversing map. But if you take it on S2 cross S2, applying on both factors, then it sort of restitutes its orientation preserving property. So we have an orientation preserving free involution on S2 cross S2, and we take the quotient with that. We obviously get a four-manifold which is oriented and also double covered by this simply connected S2 cross S2, so it has fundamental group Z2. So this is the first in this sequence of manifolds, and for the rest, I just give a Kirby diagram given here. So we just have these 3 circles. The dotted one symbolizes the one handle, and then we have these unknot which wraps around n times, and then there is a meridional 0 frame 2 handle finishing it off. Okay, and then a 3 handle and a 4 handle. So the Betti numbers are, so the second Betti number is 0 for this manifold. Okay, so these are the manifolds appearing in this exceptional list, and so the verification of the theorem would be. Say it again. It's, I don't know. I don't remember. Okay. I don't know. Still. Some stupid Four-Manifold simply connected. Okay, so how do we distinguish these guys? So that's the question, and the methodology we can use is to appeal to some smooth invariant of Four-Manifolds, and the best bet today is to consider Seiberg-Witten invariants, and for us, Seiberg-Witten invariants are just functions on the second cohomology, and I will not go into the details at all. I just remind you that the way these functions are defined is to pick a cohomology class. If it is not characteristic, we just declare the value to be 0. If it is characteristic, then we consider a corresponding spin C structure, actually corresponding all the corresponding spin C structures, and then we set up some PDE using this structure, and we count in some intricate way the number of solutions for this PDE. So this is what we would like to do. And here is one important fact about this function, that there is a number associated to a manifold and a characteristic cohomology class, namely this 1/4 k squared minus 3 times the signature plus 2 times the other characteristic of the manifold, and this number has a particular significance in this theory. This describes the expected dimension of the solution space, and we can turn this space into a number provided this dimension is even. So if it is odd, then the whole invariant is not that useful. So a little arithmetic tells you that this is congruent mod 2 to the B2 plus invariant plus B1 plus 1. Remember, we are considering Four-Manifolds with finite cyclic fundamental groups, so the B1 will be 0 in our case. So the Seiberg-Witten invariant somehow is meaningful only if the B2 plus invariant is odd. On the other hand, in the theorem, we didn't specify this B2 plus, so the trick what we learned from this paper of Levin, Lidman, and Piccirillo is that that's okay if the invariants are 0 on a manifold with some fundamental group, because you still have the hope to go to the universal cover, and then hopefully if the universal covers are distinct, then you can deduce that the manifolds are distinct, and this is exactly what happens here. So suppose that we have two Four-Manifolds X and Y with non-trivial fundamental group, and consider the universal covers, and it's a very simple observation to show that if they are diffeomorphic, then the universal covers are diffeomorphic. So if you can distinguish the universal covers, you distinguish them. And so it turns out that, so the conclusion is that we sort of take our potential manifolds, let's stick to the pi1 being the group of two elements, so Z2, we sort of classify our manifolds into two big classes. The ones are which have B2 plus odd, so the usual Seiberg-Witten invariants on them hopefully give some information, and this is exactly what happened, and these cases were worked out earlier, for example, by Rafael Torres, and so we will not sort of touch those circle of manifolds. And the other guys where but the B2 plus is 2k, it's an even number. We can go to the universal cover, and by some very simple magic, it turns out that those B2 plus invariants will be always odd, so we are back into the potential application of the Seiberg-Wittens. Although downstairs in the actual manifold, they don't carry any information at all. So this is what we will do, and so the lesson is that what we would like to do is to construct simply connected Four-Manifolds which can be presented as universal double covers of other guys, which just says that we need orientation preserving involutions on them which act freely on the manifold. So, except instead of looking for exotic structures on symplectic manifolds, you also look for this extra structure of like having a free involution. And this is what we did. And so instead of telling you the whole story, I'm just taking a little piece of it, and we will concentrate on the case where the B2 is equal to the B2 plus and it's equal to 1. So such manifolds were really studied for a long time, and their name in algebraic geometry is fake projective planes. So a fake projective plane is a complex surface which has the same rational homology as CP2, but it's not CP2. And that was a long-standing question whether such objects exist or not. And in the 70s, one example was constructed by Mumford, and sort of surprisingly and uncharacteristically of dimension 4, there is a complete and well-described answer for the question of like how many such fake projective planes do we have. Even more surprisingly, the number is suspiciously round. So, I mean, you would not guess. It should be some weird number. And it turns out that up to diffeomorphism, there are 50, and up to biholomorphism, there are exactly 100. So every guy comes with 2 complex structures. And this is a result based on significant work of Prasad and Jung, and then some computer search based on their fundamental groups by Cartwright and Stegert. And these are all classified through their fundamental group, and all these groups are infinite. Indeed, the universal cover of all these manifolds are the same complex. This is just the complex disk in the complex 2 space. If we just want to sit on this bandwagon, we just say that, from the smooth point of view, fake projective planes are 4 manifolds which have the same rational homology as CP2 or CP2 bar, and we would like to understand whether they admit lots of different exotic structures. And of course, the answer will be yes, they do. And so I pick one particular example where we just take this L2, the quotient of S2 cross S2 by this free involution, and connect some it with CP2 or CP2 bar. I should stop for a moment and realize that although we are considering oriented manifolds, but it's a fact that X with one orientation and with the other orientation admits the same number of smooth structures. I mean, the orientation is sort of an extra choice which you can make later after you fix the smooth structure. So it doesn't really matter which one we consider. And for technical reasons, we would like to construct the manifolds L2 connected some CP2 bar, so more precisely, manifolds homeomorphic to this smooth manifold. And we just realized that their double cover, that the double cover of this manifold is homeomorphic to CP2 blown up in 3 points. So I should add that exotic structures on this particular topological Four-Manifold were already known before. It was done by Scott Baldridge and Paul Kirk, and then Fintushel and Stern had a version of exotic structures. Now what we have to do is to sort of look into their construction and sort of tweak it a little bit, so we also get this orientation preserving free involution on them. And it turns out to be not so challenging, and so I would like to sort of give a pictorial idea of what the proof involves. So as before, as in most of these constructions, we start with 2 copies of T4. I mean, we usually take 2 copies of anything, so there is an obvious Z2 action in the result. We only have to make sure that when we glue them together, then we are gluing with an involution which is also fixed point free. So the construction goes as follows. We take T4, and so this is like a product of circles, and the product of the first 2 circles is symbolized by this horizontal line. This is one torus inside T4. And the product of the last 2 circles would be a vertical line, but I didn't draw that because we sort of take, instead of the usual torus representing the fiber class, we take a braided torus representing twice the fiber class. In a way, so this is not so hard to imagine. So we leave out the last S1 factor in the 4 product of S1s. So in this 3-manifold, this third S1 factor. Instead of taking that circle, we just take a braid instead of that, a 2 braid, and that will give us this torus. So we have 2 tori intersecting each other in 2 points, and then we have, of course, the other 2 tori in T4, and I just symbolize them by these crosses. So one cross symbolizes 2 tori intersecting in 1 point, where you take the first and the third S1 in T4, and the second and the fourth, and so on. So we have plenty of tori, and so what we do is we take these 2 intersection points in each copy, we resolve one of them, so we just smooth it, and we blow up the other. So the little circle is about to indicate that we just blow it up. So we have 2 copies of T4 blown up each in 1 point, and they contain a genus 2 surface, because we just resolved, and the self-intersection of these genus 2 surfaces are both 0, because it's a little homological computation. So we can sort of delete their neighborhood and glue up the boundaries by this capital phi, this gluing map. And all we have to be careful about is it has to be an orientation reversing map. It has to be fixed point free. And we would like to pick it in a way that somehow what's contractible on one side should meet the circles which are not contractible on the other side, and then in some way we kill all the homotopies. I know it sounds like a thriller or something, but that's what we do. Of course, it will not work, because there are just too many homotopies. We have a 4-dimensional fundamental group in one side, a 4 in the other side, and in the middle you have a rank 4, say, in homology, so it's just too much. So what we have to do is to perform some torus surgeries. So we just take out little neighborhoods of these tori on one side and on the other, and do some surgeries which reduce the pi 1 to a rank 2 group on one side and the rank 2 group on the other, and then pick the matching in a way that everybody kills at the end. It's like a Shakespearean play, like, nobody survives. Not in the fundamental groups, I should add. Okay, and then a little yoga on the Euler characteristic and the signature tells us that this is exactly one of those examples of exotic threefold blowups of CP2, where now there is a visible Z2 action, and then we get our result. I should mention that when we do the torus surgery, this is sort of a generalization of the usual 3-dimensional Dehn surgery. Instead of doing it along a loop, we do it along a self-intersection 0 torus. And we have some freedom on performing them, and this freedom is reflected in the Seiberg-Witten invariance of the Four-Manifold upstairs. So this is how we can get infinitely many such examples. Yeah, so this is what I already explained. And so, of course, to get strange copies of fake CP2s is easy. You just take the regular CP2 and you connect some with something which brings in the fundamental group. But we are shooting for something which are irreducible in the 4-dimensional sense. So if we would decompose them into a connected sum of 2 Four-Manifolds, then one of them should be at least homeomorphic to S4. And these examples all have these properties. So this is how we create an infinite family of those. And I should add that these are very, very different from the fake projective planes of algebraic geometry. First of all, they have fundamental groups, and the complex surfaces, they have all infinite fundamental groups. But more importantly, none of these are symplectic with either orientation. So, of course, with the orientation where we have a negative definite form, that's not a surprise. There are no such complex surface, but even with the opposite orientation, they are not complex, or not even symplectic. Okay, so then you might ask, so we see that there are many other fundamental groups which can play the role of the fundamental group of a fake projective plane. So what are those groups? Which groups can appear in this way? And so the other result I would like to mention today is that we can sort of inject fundamental groups into these manifolds. So the statement is that, that we can construct infinitely many exotic, so homeomorphic, non-diffeomorphic, fake projective planes, provided the group, the fundamental group, looks like some group cross Z2, where this some group is a fundamental group of a rational homology 3-sphere. So this is a wide class of groups, but notice that there is always this Z2 hanging around because the technology is to go to the double cover. And so the idea how to insert a fundamental group comes from this construction we call circle sum. And this is a very simple operation. So we start with a simply connected example with a free involution. And we take a circle which is invariant under the Z2 action. And for a rational homology sphere Y, we construct S1 cross Y, another four-manifold. And it also has a free Z2 action. We just take the antipodal map on the S1 factor and nothing on the Y. And then we pick one circle, again, invariant under the Z2 action, and we just sort of glue them together. So we take out tubular neighborhoods of these circles, and we patch them together in a way that the Z2 actions patch together. So we get this X circle sum S1 cross Y, which then turns out to be the connected sum of S with SY, the span of this three-manifold, and this is where the fundamental group will come from. And then we have to do the usual yoga of taking the quotient by the free Z2 action. So this will double the fundamental group, and you have to understand whether it's a semi-direct or direct product, or there is a little bit of an algebra there. Okay, so that's what we get, and this is how we can verify this theorem. For the general case, we follow something very similar. Instead of T4, we have to take a higher genus surface, cross the torus, and sometimes we have to flip the orientation. We have to blow up to get all the examples. If we would like to have irreducible examples where we didn't consider that, but two students of Inanj spent considerable time of doing a systematic study of irreducible ones. The exceptional cases for which we don't know the answer correspond to the fact that their universal covers are four-manifolds for which we don't know whether exotic structures exist at all. So, and we would need a little more than that. We would need an exotic structure or many exotic structures with this orientation-preserving involutions. So that's what blocks us, and I hope, in one day that 7 will become 6 and 5, and, When I was young, we were taught that, present-day communism is on 1/7 of the Earth. But there will be a day when it will be 1/8 and 1/9 and 1/10. And guess what? They were right. Okay, so this is about the story of how to construct exotic manifolds. And there is this other, maybe more philosophical or practical question, like how do we detect exoticness? What's the geometric reason their smooth structures are different? What does the Seiberg-Witten invariant measures? And this is what I would like to talk about a little bit. It will be short. So one guess might be to understand better the genus function of the four-manifold. So what is it? This is a function, the second homology. And for a fixed homology class, we take all the surfaces, oriented, embedded, smoothly embedded surfaces representing that homology class, and we just take the minimum genus among those. And that gives us a function which we very poorly understand. Actually, we are planning to have, so the collaboration will have this summer school in the summer in Trieste, and we are planning to talk about this function a little more. And as I'm talking about summer schools, I should mention that last summer we were fortunate to host the collaboration summer school in Budapest. And I think it was a great, I enjoyed it. I hope others had a great time. We had great lecture series. We try to collect them in a volume, which is almost done. So this will make it accessible for those who couldn't participate in the event. And, I hope it sort of generated lots of connection, which is important for us, but it might be even more important for the more junior part of the community. So back to the genus function. So there is one serious constraint, namely this adjunction formula of Peter and Tom. So this tells us something about, so whenever you have an embedded, smoothly embedded surface in a four-manifold, and you have a cohomology class for which the cybergrid invariant is non-vanishing, then you have some cohomological formula on the right, which bounds the genus from below on the left. So, and we have constructions. So we have sort of a limited inventory of tools. Indeed, this function is known only for a handful of simply connected manifolds. So we know it for CP2, and I will sort of write it down in the bottom. We know it for S2 cross S2, CP2 blown up once. We notice that for a manifold and the same manifold with the reverse orientation, of course, the two functions coincide. So we know it for CP2 bar. And they indeed distinguish exotic structures. For example, if we consider CP2 blown up in 2 points, then it's not very hard to see that if we have a homology class with self-intersection 0, then it can be represented by a sphere. On the other hand, all known exotic structures on CP2 blown up twice or 3 times, they have the property that they just don't contain any sphere with self-intersection 0. So you sort of see that this function follows the exoticness. How faithfully? Well, we don't know. It is clear that we cannot hope that they will detect all exotica, well, according to my belief. So if there are exotic S4s, obviously this function will never detect the exotica of those. And so we have these fake S2 cross S2s. These are oriented four manifolds, which have the same integral homology as S2 cross S2, but potentially different fundamental groups. They have different cybergrid invariants, so they are not diffeomorphic, but they do have the same identical genus function. So, we have to do something better than that. Let me mention this fantastic result from now 30 years. It's sad. Well, that's whatever. So it just tells us that what's the genus function for CP2, and of course the most obvious next question would be what happens for 2CP2, where the whole method just completely breaks down. So let me just mention one result. So there is this. I can call it the naive bound. So you take 2CP2, then every homology class can be described by 2 integers. We can assume that they are all non-negative and say the A is bigger than B or bigger than or equal to B. And so we can sort of represent this homology class by the optimal surfaces in the 2CP2 components, and we just connect some them, and that might be the right answer. It's not surprisingly. And so there is an inequality which says that the naive bound minus the actual value is bounded from below by A minus 3B, which notice that it's interesting if A is actually bigger than 3B. So if the ratio of the 2 coordinates is large enough, then we can have a growing improvement corresponding to the naive bound. If the ratio of the 2 coordinates is not that big, then we know way less. And indeed, for the cases when E is exactly 3 times B, we could sort of see in many cases that the naive bound is the optimal one. For 1,3, the first such, the argument is very simple. It's a self-intersection 10 class. If it is we know how to represent it by a torus, because this is the cubic curve in CP2, and the other one is just the generator, just the CP1. Can it be represented by a sphere? Well, the usual Rocklin type invariant shows that we cannot. We just blow it up 9 times and then blow down the resulting +1 sphere, and we get a spin manifold with signature -8. That's too bad. That contradicts Rocklin. For the next one, when we have 2, 6, this is a little more complicated, and there is an old result of Jim Bryan from the mid-90s saying that here the naive bound is again sharp. Any surface representing that class has to have genus at least 10. Here the techniques are much more involved. It goes through a double cover construction and then an improvement of the 10-8 conjecture, 10-8 theorem, and the improvement comes from the fact that the double cover comes with a Z2 action, and that's sort of taken into account, and it improves a bit, just enough to prove that statement. And we will get back to that a little later. Okay, so I tried to convince you that this genus function itself is not good enough. For example, it will never detect a counterexample to the 4-dimensional Poincare conjecture. Here is a way to sort of refine it. So instead of taking homology classes only, we puncture our 4-manifold. So now we get a 4-manifold with S3 boundary, and we consider all knots on that boundary, and we ask what are the minimal genus, the minimal slice genus of those knots, provided we also fix the homology class. So that's a little refinement. If you run it for the unknot, you just get back the original genus function, so it adds a little more. Of course, we can substitute the set of knots with the set of links, but then we have to make sure, what kind of slice genus we have in mind, and I will not go into that. Nevertheless, we can consider the set of slice links in X, where I do mean these strongly sliced links. So they have to have these. The components should bound disjoint disks. And so here is a theorem which both statements can be viewed in 2 ways. So the statement is the following. So suppose we have a potential exotic D4. So that would provide a counterexample to the Poincare conjecture. We don't know whether it exists or not. We classify them into 2 classes, very similar to the discussion in exotic R4s. We call small or large, depending on whether this exotic R4 embeds into the standard R4 or it doesn't. Similarly, we say that potentially exotic X is a small exotic D4 if it embeds into the standard one, and it's large if it doesn't. And the statement is that for small exotic D4s, these 2 sets, the set of slice links in D4 and the set of slice links in this potential X, they are the same. And the argument is kind of simple. It just says that if we have 2 potential exotic D4s and one is inside the other one, then the set of slice links also follows this inclusion. And the idea is just an upscaled version of the trace embedding lemma. So this has something to say about the Schoenflies conjecture. So this sort of tells us that if there is a counterexample to the Schoenflies conjecture, we have no idea how to detect it using these techniques. The sliceness properties, and in fact, we can sort of upscale it to slice genera, they will be the same. So this brings me to my other belief that, contrary to the Poincare conjecture, I do believe in the Schoenflies. So I hope that, just to see the colorful personality you are seeing here, believe, non-believe. So that's for small. Once again, these are only potential examples. We don't have any single one. But there is a good news that if we have a large exotic D4, then the set of slice links is definitely different from the set of slice links in D4, under the very strong condition that these potential counterexamples should be geometrically simply connected. So it should admit a handle decomposition without one handles. Whether it's a reasonable assumption, I don't know. But it's very strong, I know, but still gives us an idea of why to propagate the study of links and slice properties of links in S3, because it might lead to a technique of distinguishing these 2 sets. Okay, so what happens with knots in various four-manifolds? So there is this little observation that in S2 cross S2 and in CP2 blown up 1 point, every knot is sliced. This is a classical result, but you can see it immediately by taking your favorite knot, frame it either 0 or 1, depending on you want to see it sliced in S2 cross S2 or in CP2 blown up once, and add a 0 frame meridional, and then with a little bit of Kirby calculus, you convince yourself that the four-manifold you created is exactly what you were aiming for, but you have this two-handle, the core of the two-handle just provides you the slice disk. So this shows that if you have an indefinite simply connected four-manifold, then every knot is topologically sliced. So it's really the question of what happens with smooth sliceness. And so in CP2, it's not very hard to come up with examples where indeed the slice genus is arbitrarily large, although you can even demand that the knot stays topologically sliced. And there is this result Marco was talking about earlier this week, that in the K3 surface, all knots with unknotting number 20, at most 21, are sliced. And you might say that, unknotting number 21, these are like all the knots we know, which is not true, but this is a big bunch of knots. But on the other hand, this 21 is very suspicious. It's very close to the second Betti number of the surface. So again, we don't know any example which is not sliced in the K3 surface or indeed in any indefinite four-manifold. So a potential answer would be that in any definite four-manifold, not all knots are sliced. There are non-sliced knots. I'm sure that this is not super hard to verify. And the potential, but very unlikely outcome is that in indefinite four-manifolds, all knots are sliced. But that might happen to sort of give some idea. So here is an amusing observation. So I talked about this minimal genus of this 2-6 class into CP2, and so it has a funny consequence. It turns out that we can use it to show that the 2-1 cable of the figure 8 is not sliced. So why was that a question at all? Of course, we would prefer to know which ones are exactly the sliced knots and which ones are not. But this had a particular attention because it was known in the mid-90s that this knot is not ribbon. So if with some ingenious technology you could show that it is sliced, then that would be the counterexample for the sliced ribbon conjecture of Fox from the 60s. Well, it has been shown by this five-fold paper of Dai, Kang, Malik, Park, and Stoffregen that indeed the 2-1 cable is not sliced. And so I would like to give you a little argument to show the same. And indeed, it's like a ping-pong game. So they've showed the 2-1 cable. We gave another proof. They used the other proof to show that some other further cables are also not sliced. And I don't have any philosophy. Why is it interesting? But so with the 2-1, let me just make one more point. So if you take the figure 8 twice, of course that will be sliced because it looks like K connected some the mirror. So you double the figure 8 in some other way, you might say that, okay, with a little help from God, it will be always also sliced, but it's not. So what's the argument? So this is the proof. So what is this? So you have to imagine that we have the 4-disk, and on the boundary, I drew the figure 8 knot by this black curve. It's a little bit isotoped to some, purposes. And then we build upon this knot the 2 CP2s. Because eventually we would like to use the minimal genus property in 2 CP2. So these 2 CP2s, how do you build 2 copies of CP2 on the disk? You take 2 unknots, which are +1 framed, like these red circles, and then you just glue 2 handles along them. So what we have to see is now a cobordism, or actually an annulus connecting the figure 8 on the boundary of my S3 and some knot on the top, which we can compute by sort of sliding off these +1 framed red circles. And this is a little bit of a yoga to convince yourself that if you do that exercise, then you will get the unknot. So we get an annulus connecting the figure 8 and the unknot in the 2 copies of CP2. And yes, so we have to identify the homology class of this cobordism, of this annulus, which is very easy to do because it just boils down to understanding the linking number of the black with the red curves. And it's, you just can follow it with your finger, and it turns out that the linking number is 3 and 1. So this annulus represents, in relative homology, the homology class 3, 1. On one end, it's the unknot, so you can just sort of finish it off, and you get a disk with the boundary figure 8. So if the figure 8 is slice, then you could finish it off by a disk, so you would get a sphere representative of 3, 1, which contradicts my earlier Rocklin type argument. Of course, this is a very convoluted way of proving that the figure 8 is not slice. But we have convoluted proofs, that's what it is. But we can sort of make the following trick. You can 2-1 cable not only the knot, by this entire concordance, and you will get, again, an annulus going from the 2-1 cable of the figure 8 to the other end. You have to understand what that knot is, and I will just tell you what it is. It's a torus knot. It's an alternating negative torus knot 2 minus 19. And it turns out that this is a genus 9 knot. So you can finish it off by a genus 9 surface. Again, we checked the homology class of this cobordism, and now we doubled it, so it's like 6, 2. So if this 2-1 cable would be, so this is what I said. I have this fantastic drawing, which I sort of plagiarized from Saint-Exupéry's Little Prince. So this is how I imagine 2CP2. There are these 2 +1 spheres in the middle. I cut off the 2 ends, and there is this blue surface, which is an annulus, going from the 2-1 cable of the figure 8. And on the other end, we have this alternating torus knot, which I drew as an unknot, sorry. And there is this genus 9 surface. So if we would be able to cap it off, then we would get a contradiction. You would think that the same argument might generalize to higher cables, but it doesn't, not on the nose. And the reason is that in Bryant's theorem, it's an improvement of the 10-8 conjecture. It's not an improvement of the 10-8 theorem. It's not an improvement of the 11-8. So we need much sharper estimates to actually, and much better understanding of the genus function of homology classes in 2CP2. So, yeah, beautiful, no? I know. So, simple question, what happens in 2CP2 if you pick the homology class 3, 2? So this is not characteristic. You don't really know how to use the Rocklin type invariants. It's easy to represent it by a genus 1 surface. Can it be represented by a sphere? I don't know. This would be very interesting to see not only the result, but how you get such an information. And a slightly related question is that you have lots of spheres in the K3 surface. They help to sort of untie knots and construct slice disks for several knots. Does this set of self-intersection of spheres in the K3 surface, does this set have a lower bound? Is the minimum finite? We don't know. The current world record is -86 for that, and we don't know whether we can beat that. I think it's a very interesting and sort of amusing question. And with that said, I would like to thank you for your attention.